Hi, my name's Andy Wood, and I work for the National Center for Atmospheric Research in Boulder, Colorado. Today I'm going to talk about current challenges and opportunities related to streamflow forecasting for drought in the U.S. It is important to start by recognizing that the U.S. has relatively strong capabilities in streamflow forecasting. These are better than in many countries, and at times and space scales that are relevant to drought. These include short-range forecasts out to 10 days and long-range seasonal and annual forecasts at lead times up to 2 years and even longer in some locations as the Colorado River Basin. The NOAA River Forecast Centers, which are the primary centers for streamflow forecasting in the U.S., are staffed with forecasters who in some cases have deep expertise over many decades regarding U.S. watersheds, and other agencies such as the NRCS and the water agencies, Corps of Engineers and Reclamation, also participate in the flow forecasting enterprise. And the USGS is one of the world leaders in streamflow and groundwater monitoring practice. These data and forecasts are critical to managing our water infrastructure from municipal scales up to regional levels. There's a growing need for an improved understanding of watershed sensitivities and even basic functioning. We need to know more about the impacts of long-term trends in climate on basic watershed yield and other quantities that are used in water supply, but also on the predictability of streamflow and our ability to make skillful forecasts. Stakeholders are concerned that climate change is driving changes in our watershed hydrology and the patterns and relationships between variables like rainfall, evapotranspiration, snowpack, and runoff, which will reduce the predictability that we've exploited over the past number of decades. We need to know more about how surface water and groundwater interact during drought and whether our models fully capture these interactions. There's a lot of anecdotal evidence that there's a drought hangover from one year to the next that leads to lower than expected runoff. If this is so, is it due to these surface water groundwater interactions that we're not representing? And how can we learn more about them and build them into our forecasting models? We also would like to know how dynamic vegetation and soil changes during a drought influence hydrologic response, in particular during other extremes, such as before or after wildfires. Our forecasting models do not currently take these factors into account. Fortunately, there are compelling opportunities to advance our prediction capability. We can make better use of subseasonal to seasonal climate prediction information. There's currently very little use of subseasonal climate forecasting and even of seasonal climate forecasting in our current hydrologic prediction practice. Many studies from the last 20 years have shown that there's usable climate forecast skill that can be found in either empirical teleconnections from climate indices or more recently in seasonal climate forecasts from global coupled climate forecast models. We need to have an ongoing interaction between climate scientists and hydrologic forecasters to steadily develop this aspect of forecasting. And fortunately, it appears that the agencies like the NOAA Climate Prediction Center are making efforts in this direction. Other opportunities to advance our prediction capability include improving our watershed modeling. We currently use relatively simple models in our operational prediction enterprise, but we can carefully add complexity to account for some of the missing processes in those models, such as including factors for dynamic vegetation, surface water, groundwater interactions, and land use change. We need research into optimal model configurations to figure out how best to harness predictability. We know that too much complexity can overly constrain the model to the point that it's not very useful for forecasting, but too little complexity in the model can't capture key processes. We also can improve our watershed forecasting by improving our observations, whether in situ or remotely sensed, as well as the techniques for using the observations to update the models, which we think of as data assimilation. There's not much use of data assimilation, particularly objective data assimilation in current forecasting practice. It tends to be handled by manual forecaster interventions and updates in the models, so there's a lot of room to apply better techniques. Finally, machine learning in recent years has been shown to perform quite well in simulating streamflow forecasting in certain situations, so there's probably ample opportunity to make use of this more generally in this enterprise. If I had to make one overarching recommendation about improving our forecasting capabilities, it's that we need to regard streamflow forecasting as an applied science, multidisciplinary with a complex set of important components. It is not only about modeling or improving models or climate forecasting or observations, but rather requires advances in many areas and expertise across multiple disciplines. The best systems are not built just by modelers, and in fact, when we've seen modeler-centric development efforts in the past, they've tended not to pan out as well as expected. Some of the elements I've talked about before in this presentation, such as improving weather and climate forecasts, but also the methods used to formulate them into model input, improving modeling and watershed observations, but also the hydrologic data assimilation techniques needed to fuse them with the model states. Statistical methods such as post-processing to correct systematic errors and to apply verification and benchmarking to forecasting systems and their components are needed. We need to transition away from manual forecasting workflows toward over-the-loop prediction approaches. And we need to recognize that forecasting is essentially an informatics challenge that involves Earth system science and bring in more people with expertise on the informatics side. In particular, I think the U.S. hydrologic prediction enterprise needs a formal multi-agency community testbed for forecasting research operations and to foster systematic development and add rigor to our efforts to advance streamflow prediction. Thank you.